We're going to continue where we left off in class today and keep analyzing situations with Newton's second law and using components. All right, essentially forces that are directed in two directions that we have to split into perpendicular parts so they make sense with our x-axis and y-axis that we chose. All right, if we look at the situation, a 70 kilogram box is pulled by 400 Newton force at an angle of 30 degrees to the horizontal. The force of friction is 75 newtons. The scenario is sketched for us, so we're going to circle the object of interest. All right, so the object of interest in this case is our box. Okay, this is what I am curious about. If we look at this, we have the rope is interacting with it, the earth, and the floor. Okay, basically there's two forces here. There's the support force that is exerted up, and there's friction. Okay, so I'm just going to put in here times 2. All right, the support and friction. So next what we're going to do is we are going to represent the object with a dot. As you can see, we've labeled our object box, and we've put a positive x and positive y direction in there. So now what we're going to do is we're going to draw all the forces exerted on this. All right, if I look at this here, we have the force of the rope, which is at an angle. All right, so I'll label this force of rope on object. Okay, and this angle here is 30 degrees. We also have a frictional force that impedes the motion, and that's pointing to the right. All right, and that is the force of the floor on the object, and that is the frictional force we spoke of earlier. We then have the force of the floor, which is exerted upwards. Let me draw this in here. This is that support force in which we discussed. So the floor on the object, and I'm going to put an S for support. And then we have the earth. Now keep in mind the earth is going to be the combination of this one pointing up and the part of this that's pointing up too. So you have two parts pointing up, they add up. Since the box is going to accelerate to the left, the vertical forces should all end up equaling 0. So I'm going to draw a longer line so that this line roughly resembles the force of the floor plus the rope, the part of the rope that points up. And we'll label this the force of the earth on the object. Alright, now to be consistent, we know that this is accelerating to the left. My change in velocity arrow is pointing to the left. And if we look at this, my unbalanced force is pointing to the left. Alright, so now we have our motion diagram, our force diagram. We know the vertical forces are balanced. We know the horizontal forces are unbalanced. And now we're going to write out Newton's second law. Before we get writing Newton's second law, over here on the right-hand side, I drew a diagram of just the force of the rope on the object because I want to talk about this for a second. So we know that the force of the rope pulls to the left and actually pulls up. So we have to find out exactly how much of the force of the rope pulls to the left and pulls up. So I'm going to draw in what are called vector components. All right, in this case it's a force vector, so there are force components of the force of the rope. The rope partly pulls up, so I'm going to call this the force of the rope in the y direction. And it partly pulls to the left, so I'm going to draw another arrow representing how much it pulls to the left. Label this force of the rope in the x direction. Now we're going to use a little trig to come up with an expression for the force of the rope in the x direction and the force of the rope in the y direction. If you recall, the y direction is the opposite side from this angle. The x direction is the adjacent side. Thank you, EF Educational Tours. I really don't need that. The force of the rope itself is the hypotenuse in our right triangle. Okay, and it's a right triangle because the vertical direction, the y direction, is perpendicular to the x direction. So to determine an expression for the y part and the x part, we're first going to deal with the y. So opposite over hypotenuse is going to be sine. So we have the sine of 30 degrees will equal the force of the rope in the y direction divided by the force of the rope on the object. So in general, the force of the rope in the y direction will equal the force of the rope on the object times sine of 30. All right, to repeat for the x direction, it's going to be cosine of 30 is equal to the force of the rope in the x direction divided by the force of the rope on the object. Okay, if I multiply through by the force of the rope, I have the force of the rope in the x direction will equal the force of the rope on the object times cosine of 30. So now if I go into my diagram and draw in the two components, okay, we're going to be able to set up Newton's second law horizontally and vertically. So if we look at this, horizontally we have two forces and we know the acceleration is pointing to the left. So I'm going to have AX, the acceleration in the x direction, is equal to, well, the sum of the forces in this case are going to be the force of the rope in the x direction minus the frictional force of the floor on the object. Okay, and that's friction divided by the mass of the object. In the y direction, we know that the force of the floor that's exerted by the surface plus the force of the rope vertically will be equal to the force of the earth. And looking at our motion diagram, we know that the acceleration is horizontally, which means vertically there is no acceleration. So the acceleration in the y direction, AY, is going to be equal to 0. And the sum of the forces will be the force of the floor on the object, and that's the support force, plus the force of the rope in the y direction minus the force of the earth on the object. And this whole thing will be divided by m. Well, if I multiply m through both sides, we're going to find out that the m, if I multiply m here, this will divide out with the m here, and if I multiply m times 0, okay, anything times 0 is 0. So it's going to be 0 is equal to the force of the floor, which is the surface, plus the force of the rope in the y direction minus the force of the earth. Okay, now to figure out the acceleration. So if we look at this, the force of the rope in the x direction is given by the expression the force of the rope cosine of 30. So we're going to put the force of the rope in, which we know is 400. So we have 400 newtons times cosine of 30 degrees minus the frictional force, which is 75 newtons. And this whole thing is divided by 70 kilograms. When we substitute all of this in, we find out that the acceleration is going to be 3.88 meters per second Okay, now we have the acceleration of the object. So when you're writing in force of the rope in the x direction, you have to include that cosine of 30. You can't just leave it as 400 newtons. Alright, I need a little more space, so I scrolled down a little bit here. So we're solving for the force of the floor that's exerted by the surface on the object. Alright, so this is going to equal 0 is equal to the force of the floor on the object plus the y component. Now looking up here, we go back, we find that the force of the rope in the y direction is going to be the hypotenuse, which is 400 newtons, times sine of 30, okay, minus force of the earth is the mass, so 70 kilograms, times 10 newtons per kilogram. And as we calculate all this out, sine of 30 is 0.5, so 200 newtons minus 700 newtons. And if we add the force of the floor on the object, we find out by solving for the force of the floor on the object, we get 500 newtons. So there you have it.